Welcome to linear algebra class. In this class, we are going to talk about important concepts in linear algebra and data analysis, machine learning, and so on. So in the first video, we are going to start with part 1. So we will be talking about few important concepts that talk about the introduction to linear algebra. So part 1. So this chapter is very important, especially if you need a refresher on the concepts in linear algebra. So first and foremost, so what are the highlights of linear algebra? So in linear algebra, we are trying to solve the matrix problems. And if you believe these linear algebra problems start when we enter high schools. Perhaps you remember the problem, something like this. 5 oranges plus 3 apples. They are for $10. And then say 3 oranges plus 2 apples are for $15. Now we need to solve these two equations and get the values of oranges, what is the cost for each orange, and what is the cost of each apple. Now this problem can be formulated in terms of linear algebra problem, something like this. I'm going to write this down as 5, 3, 3, 2. Oranges, apples is equal to 10 and 15. Now this problem can be viewed as a very simple problem. If I were to say just 5 oranges are for $5, then clearly you can say 1 orange is for $1. So what did I do? Implicitly, in this process, to find the cost of an orange, I did this. So the coefficient on the left-hand side, I inverted the coefficient and multiplied that onto the right side. We have to do something similar in the case of matrix. So oranges and apples is equal to, we are going to have inverse of this matrix. This is no longer a scalar number. Inverse 10 and 15. Assuming this matrix, which are a bunch of numbers stacked in a square or a rectangular fashion, is invertible, which means we can do this operation. Assuming matrix is invertible, we can find the answer for the orange and apple. So, and once again, quickly, this is a row. This is a column. So this is 2 rows, 1 column, 2 rows, 2 column, 2 rows, 1 column. So for matrix multiplication, the required condition is the column of this matrix should be equal to the row of the second matrix. So this problem can be written as one of the very fundamental problems in linear algebra. So this matrix, if I were to say as A, if X is my unknown and B is my known, first class of problems is trying to find or finding X or solving AX is equal to B. This is the first type of problem that we would start to look at when we study linear algebra. And this inversion, this A inverse, and let me put it like this, A inverse may be possible, may not be possible. A classic example I want to show you is, think about it like this. If I were to give you 5 oranges plus 3 apples is equal to $10, and 10 oranges plus 6 apples is equal to $20, you will see this equation in the matrix form can be written as 5, 3, 10, and 6. Same as previous one, orange and apple, 10 and 20. If I were to solve this equation for some reason, we would realize that this equation cannot be solved. And a geometric way of looking at this equation is something like this. So this is line number 1. This is equation 1. And this is equation 2. Just imagine if I were to plot these two equations on an X, Y plane. Or if I were to draw this equation onto XY plane, we would notice that both of these lines, they coincide. They will have the exact same slope and they will have the exact same intercept. So what it means is, if I were to draw the line, this is the equation 1. And if I were to draw the line number 2, they are one and the same line, because the second equation, if you were to multiply the first equation by 2 times, you get the second equation. So this matrix is not invertible. What it means is, we do not have 2 independent equations. In other words, we have 2 variables, orange and apple, and only 1 equation. So the problem cannot be solved. Now, next class of problem we will study, and this is an important problem in linear algebra, is, let's look at some sort of a matrix. And this is, here we are going to just deal with matrix. So we are not looking at equation. What I mean by that is, I'm not looking at Ax is equal to B equation. There is no B, no RHS. Instead, what I want to do is, and X again is the unknown. Okay, there is no RHS, but X is unknown. And this equation, I want to write it something like this. If I were to write AX is equal to lambda B, where AX is equal to lambda X. Some observations here. Lambda is unknown. X is also unknown. Now, this problem, I want to solve somehow. I want to find X and lambda. Now, as we try to get into solving this problem, let's try to visualize what this problem is. So if you think about it, A is the matrix that is known to us. Say again, if I were to go with the previous example, and I'm picking up some numbers, 3, 5, 2, and say 1. This is my matrix A. Now this is going to be multiplied with another matrix, x1, x2, x3, x4. And on the right hand side, I'm going to take the simple case to start with. I have lambda 1, 0, 0, lambda 2, and x1, x2, x3, x4. So probably you have seen this problem as something called as the eigenvalue problem. So this is called as eigenvalue, which are lambdas and eigenvectors, which are pairs x1, x2, corresponding to first lambda 1, x3, x4, corresponding to second eigenvalue, which is lambda 2. Now this is the eigenvalue and eigenvector problem, and let's try to give some geometric interpretation to all this complete problem. So let's look at this matrix A. So this is a two-dimensional matrix, and I'm gonna I'll try to show this matrix on the x-axis and y-axis. So I'm trying to plot this matrix. Now these are all real numbers, and again there are two real numbers. So this is called as R square because there are two real numbers. One real number line is here. This is R1, and the second real number line is R2. So this space is called as the real space in two dimensions. Now, what I'm going to do is I will try to somehow plot these points. So I'm going to plot these points. So first point that I want to plot on this plot is maybe 3 and 5, and the second line which I want to plot maybe is 2 and 1. So which is 2 and 1. So these are two lines, 2 points essentially that I have plotted on R1. Geometrically, if you think about the eigenvalue eigenvector problem, we are trying to look for one constant that would scale this matrix. So just to give an example, let me try to give you just a simple idea. So 3, 2, then I have 5, 1. And if I multiply this by, I'm just going to say x1 and x2, then I have an equation which is first row, first column, and second row, first column. So this equation is going to become lambda 1 x1 lambda 2 x2. So this is nothing but a scaling factor. This is a scaling factor. A matrix, actually what it does when you multiply a matrix, this is a vector, by a vector, what it does, it scales the vector. Essentially, it rotates the vector in the two-dimensional plane because there are 2 dimensions. But as you can see, after rotation, the matrix for these particular values of x1 and x2 results into just scaling. So think about if you have a vector, and if this vector is x1 and x2, if this vector is x1 and x2, and this is an eigenvector. When this eigenvector multiply this matrix, what you get is you get a scaled version of the vector. So this is the eigenvector, and when eigenvector multiplies the matrix, it gives you the scaled version of eigenvector. And that is an important observation. So this is something we will discuss in detail when we try to solve the problems. And in case if you are wondering, I don't want to take a shortcut when I try to solve this equation. Let me expand this equation, that will make it clear. 3, 5, 2, 1. x1, x2, x3, x4 is equal to lambda 1, 0, 0, lambda 2. Again, x1, x2, x3, x4. First row, first column. So 3 x1 plus 5 x2 is equal to first row, first column, lambda 1 x1, 0 x2 first row, first column. Then I will have to repeat the same process because I'm going to get a 2 by 2 matrix. So, and I should have written this something like this: first row, first column, first row, second column, second row, first column, second row, second column, so this is the product. I need to repeat the same process. You need to do the same thing on the right hand side, but right hand side is a little bit easier. So I'm gonna show this product over here. First row, first column, first row, first column, first row, second column, second row, first column, second row, second column. So essentially, when we are trying to solve the eigenvalue problem, we are trying to solve this set of equations. And this problem can be stated in pairs. So we are trying to solve the eigenvalue problem. Essentially, we are trying to solve this set of equations. Next problem in the linear algebra is trying to solve an equation which is of the form, and this is another important problem, from the form is A is a matrix V times sigma U. Now, one important part that this matrix is multiplied by an orthogonal matrix or orthogonal vector. So this is orthogonal. This is also orthogonal. So this problem is applicable to square and rectangular matrices. Now, some of you may raise this question: what happens if A matrix A in this case is square? Then this reduces down to nothing but the eigenvalue problem. But this is the most general problem, and this is written as singular value decomposition. So singular value decomposition. In simple words, loosely speaking, the eigenvector and eigenvalue problem for the rectangular matrix is nothing but the singular value problem. And this is an important problem. This is where linear algebra meets data science and machine learning. When we are trying to solve any data science problem, we are going to have huge matrices. And typically, the problem would be of the form, since it's an orthonormal matrix. So I need to say orthonormal. What do I mean by orthonormal? Which means each vector of this matrix V and U. So these two vectors, they have the modulus 1 and they are perpendicular to each other. So this problem can be written as V. So I'm going to write this down as V transpose. So I need to write this down. Since V and U are orthonormal, V inverse is equal to V transpose. A simple example is 1, 0, 0, 1. If you were to invert this matrix, inverse of this matrix is again 1, 0, 0, 1. So this equation A, B, V transpose is equal to sigma U V transpose. And this, actually, I need to, this problem is the crux of something called as principal component analysis. So finding the most important subset of a huge data set, that basically trying to find what are the principal components of any particular problem. And this is used in lots and lots of applications, especially if you are trying to solve some problem experimentally and you have a lot of experimental data. How do we reduce the data? How do we separate out the signal from the noise? And that is all principal component. Now, next class of problem is minimization problem. So think about this problem, something like, let me start with the oranges. Now I have 3 oranges plus 2 apples is equal to, say, $10. 4 oranges plus 3 apples is equal to $15. And then maybe I have 2 oranges plus 1 apple is equal to $5. So right now, what I have is I have more equations. So I have 3 equations. So I have 3 equations than unknowns. And unknowns or orange and apple. So what's going to happen is if you were to draw this equation set, if you were to represent this on line in a x and y plane, most likely what would happen is you are going to have 3 lines. So this line I'm assuming for equation 1, this line for equation 2, and this line for equation 3. So if you look at first 2 equations, since this is the point these 2 lines intersect, that is the solution. If you look at the second set of 2 equations, this is the point where the second set of line intersects, that is the solution. And then you have this equation wherein 2 lines intersect somewhere over here. So how do we solve this problem? So what we want to do is we want to find out a point, sort of an optimal point, which is sort of an equidistance from these 3 possible solutions. And that is called as the least square solution. And that problem can be written as A x, and here we will say finding out the best possible x that fits the data, best possible x that fits the data. Now, a slightly extended version of this problem is something like this. Many a times, we have to express the problem as a minimization problem. So this problem is minimization of AX. This is called as the norm divided by the norm of the vector itself. And that minimization problem would be used in a lot of cases. Specifically, somewhere this is related to equating the first derivative to 0 to find some sort of minima. So there is some relationship between the concepts in calculus and the concepts in linear algebra, specifically applied to the data science, but that is the condition. The last type of problem is we want to factor the matrix. Now, what do I mean by factorization? So if you have a matrix A, I want to write this as a product of 2 matrices. So this is what is called as factorization. Most commonly used factorization is I want to express this matrix as a matrix with some columns and some rows. And based on what technique you use, there are different matrix factorizations available. And one of the reasons factorization is used is for simplification. So these are some of the important concepts in the first part that we are going to study in our subsequent lessons.